Let's look at combinations of functions and composition of functions. First, we're going to talk about domain of a function. We need to find that. And adding, subtracting, multiplying, and dividing functions, and then looking at what's called composition of functions, and hopefully give you an idea of why we need to look at that, those things. Domain is an important concept in mathematics. It is critical to know what can actually be used for your independent variable. And that's really what we're talking about, the set of possible values of the independent variable. When you're looking at real data, a lot of these functions that we look at that may model real data, the function itself may have a domain like all real numbers, but the real data, that doesn't really apply. You might only be able to look at it for a certain range of values. So that is why we really need to always be mindful of what the domain of a function is. Let's look at a couple of examples here. It says determine if the following are in the domain of the given function. Well, one way we can do that is we can check to see if when we plug in the value, we have any issues. So we plug in 8 for x here. We get 8 over 5. No problems, right? We have an input of 8, an output of 8/5. That doesn't seem to be a problem. Let's try plugging in 13. We get 13 over 13 minus 13. 13 over 0. Uh-oh. I think the world just blew up because we know we can't divide by 0, right? So that's what I was always told by math teachers. If you divide by 0, the world will blow up, right? No. So this is not okay. So x equals 13 is not in the domain. I guess I should actually answer the question for the above one too. X equals 8 is in the domain of f of x. So we had a problem there because we got 0 in the denominator, right? Let's try this one. Let's try plugging in, oopsie, our function name here is g, so we should use that, g of 8. In this case, plugging in 8 gives us a square root of 8 minus 4 plus 8. Square root of 4 plus 8 is 10, right? 2 plus 8. So no problems there. X equals 8 is in the domain of g of x. Now let's plug in x equals 2. G of 2, square root of 2 minus 4 plus 8. Square root of negative 2 plus 8. Ooh, that's not real. There's no number that you can square and get negative 2. So the square root of negative 2, there's no real number you can square and get negative 2. So that's not a real number. So that means x equals 2 is not in the domain of g of x. What were our trouble spots that we saw in these two examples? First, 0 in the denominator. Any value that results in 0 in the denominator must be excluded from the domain. And our second problem was a root that gave a negative, that had a negative inside of it, right? So any value, oh my goodness, should be that. Any value that results in a negative inside an even even root. So a square root, a fourth root, a sixth root. Can't have negatives inside any of those. It's okay to have a negative inside a cube root or a fifth root. Must be excluded. Many times when we are talking about domain, we are talking about what do we exclude, and then it's everything else. Okay, so in this case, these are the two things that we're looking for. There are other types of functions that we need to consider the domain and in a different way, but things we haven't really studied yet. Things like logarithmic functions have a special thing for their domain. But for right now, we primarily are looking at things like these are this first one's a rational function. The second one is a root function. So those are the two big things that we're looking at for right now. Find the domain of this function. So g of x here, there's no problem or issue with anything in the numerator, right? What our problem is that x minus 8 cannot equal 0, which means x can't equal 8. So the domain, if you write it in interval notation, is everything on the entire number line except 8. The way we write that in interval notation is negative infinity to 8. When we use a parentheses, that 8 is not included. So we're not including the 8 in this interval, negative infinity to 8. That's everything below 8. And this other interval here, not including 8, but everything bigger than it, 8 to infinity. The union is an OR. So the domain would be all x values in either of those intervals. Let's take a look at this one. Are there any issues with any x value that we would plug in here? Is there anything that we cannot plug in for x? And the answer is no. Any number is fine if we don't have a context to this that would make us say, well, wait, that's a parabola. If that parabola has a restricted domain because of time or whatever, we'll talk about that a little bit more as we get into studying these functions a little bit more. But no, there's no issues or restrictions there. On this one, with the root, our square root, our x plus 2 has to be greater than or equal to 0. It's okay for a square root to have a 0 inside a square root. So we can have the x plus 2 equaling 0, but it also has to be greater than 0 so you don't have that negative inside the root. Subtract 2 from both sides and you get that. The only thing to be careful of when you're solving an inequality, remember, if you multiply or divide by a negative, you have to switch the direction of the inequality. So just be careful with that. Remember that rule. X greater than or equal to negative 2 would be this in interval notation. We use a bracket there to indicate to include the negative 2. J of negative 2 in this case is 3 times the square root of 0 minus 4, which is negative 4. And that's okay. No problems there. And anything bigger than negative 2 would be okay inside that root. On this one, we have to be really careful because typically we would say, oh, we have inside a root, we need x plus 2 to be greater than or equal to 0. But we're actually running into two issues here. We're running into the root, not letting that be negative inside the root, but we also can't have the 0 there in the denominator, so we actually have to get rid of that equal sign. Because if x minus 2 is equal to 0, you have the square root of 0 in the denominator, which is 0. You get 1 over 0, and that's not okay. So here we need x to be greater than 2 when we add 2 to both sides. So 2 to infinity. So there's a couple of examples of domain. Let's talk a little bit about adding functions, subtracting functions. I don't think any of these definitions will surprise you. f plus g of x is f of x plus g of x. Same thing on these, the subtraction, f of x, multiplication is f of x times g of x. This is f of x divided by g of x. Just make sure that g of x is not 0 there. Okay. So no surprises there, I don't think. Let's practice using some of these. F of x equals 2 plus 1 over x. G of x is that 1 over square root of x minus 3. It says find and determine the domain. Well, first let's add them. F plus g of x is going to be f of x plus g of x. Not a lot we're going to be able to simplify or combine here. When we talk about the domain of these, we want to be really careful. The domain needs to exclude any values that had to be excluded originally. So when we talk about the domain of f here, x cannot equal 0 because that would give you 0 in that denominator. And for g, the domain of this one, g, is that x cannot equal 9. And the reason for that is the square root of x minus 3 cannot equal 0. So that means the square root of x cannot equal 3. So square both sides of that and x can't equal 9. But we also have this issue that x has to be greater than or equal to 0 because of that root. And so the domain of g, so let's write this out a little clearer. Domain of f is negative infinity to 0, union 0 to infinity. The domain of g is negative, oh no, we can't have any negatives because that would give us a negative inside a root. We're going to go 0 to 9, union 9 to infinity. So in this case for g, we had both a 0 in the denominator when x is 9, and we had the root to consider. So basically we're saying x had to be positive, but it can't be 9 also. So we have to exclude that. That means the domain of f plus g is sort of the combination of those. So f doesn't allow us to include, g doesn't allow us to include any negatives. So we have to sort of get rid of this part. And f doesn't allow us to include, so g doesn't allow us to include any negatives. F doesn't allow us to include 0. So we can't use that. But the rest of that is okay. So our answer here will be 0 to 9, union 9 to infinity. And if you look back at our actual result that we got here, that kind of makes sense. You can't have x equals 0 because of this guy. You can't have negative x's because of that guy. And you can't have 9 because of that denominator. Okay, let's multiply these here. Two plus 1 over x times 1 over square root of x minus 3. We can distribute that if we want to get 2 over square root of x minus 3 plus 1 over x times root x minus 3. And the domain is going to be the same. Same issues, 0 to 9, union 9 to infinity. X equals 0 doesn't work because of this guy. X equals 9 doesn't work because of this. And any negatives have to be excluded because of the root. Let's do the division here. It's going to be 2 plus 1 over x over 1 over square root of x minus 3, which is, remember when we divide by a fraction, we multiply by its reciprocal. So we have that. And I suppose we could distribute that out if we wanted. 2 root x plus root x over x minus 6 minus 3 over x. Okay? So that would be our division. Let's think about the domain here. One thing we have to be careful of is that the domain of what we see as a result here, if we were just given this function, the domain of this would just be x can't be 0 and x has to be greater than or equal to 0. So combining those would give us 0 to infinity. Can't have 0 in the denominator because of this guy, and you have to have positive x's because of that guy. I guess this guy makes it an issue too. So, but the problem is that before this was all simplified, x equals 9 is still a problem. And so we can't include any values that were originally excluded in the function. You might have to exclude some values that were originally included, but you can't include anything that didn't work originally in the original functions. So that means we still can't include the 9. This one, if we just said 0 to infinity based on what we have as our result here, the 9 is still included, but we cannot include that 9 if it wasn't able to be included when in the original functions. So the domain should never be bigger, should never include more than what you started with when you're doing this algebra of functions. Be careful there. All right, last thing in this video we're going to talk about is composition of functions. Sometimes you'll hear this referred to as fog because it's got this little circle looking thing that is almost like an O, or we could do it this way. So sometimes students will say fog or goff if you flip the order. So what this is when a function g of x is inside another function. And this is defined this way. We do have to have g of x in the domain of f, otherwise you can't plug it in. We'll talk about this domain in a second. We'll come back here. Let me show you what this fog, f composed with g, is. F composed with g of x could be written f of g of x. And I usually do that just to help me see what is happening here. So f, what we're doing is, what we're saying is we are going to take the g, whatever it is, in this case 2x minus 1, and plug it in to the f. And so that means everywhere I see an x in f, I have to put 2x minus 1. That means the 2x minus 1 there is going to replace that x. It has to get squared, and then we still have the plus 1 there. It'd make more sense if I did this. So the 2x minus 1 goes in place of the x. The g goes in place of the x in f. Multiplying that out, 2x minus 1 times 2x minus 1, and then plus 1 on the end. 4x squared minus 2x plus 1 plus 1. 4x squared minus 4x plus 2 is what f composed with g is. Okay, let's do, I didn't leave enough space here, I hope you did. Let's do g of f of x. We'll come back to the domain in a second. That means g of f of x, g of, okay, so f gets replaced, f of x is the same thing as x squared plus 1. So that is what I am putting inside g. That is going to be, all right, g is 2. In place of that x, I'm going to put the x squared plus 1. And then I still have the minus 1 on the end, right? 2x squared plus 2 minus 1 simplifies to 2x squared plus 1. So that is those two compositions. That's how composition works. You're literally plugging a function in to the other function in place of the x for that function. Let's talk about domain. Let's go back to review what it said up here about domain. The domain of the composition is the set of all x such that x is in the domain of g. What that means is you have to be able to plug this x into the g, right? Because you're evaluating g of x. You also have to have g of x, so any output of g, you have to be able to plug that into f, right? Because that's what we're doing when we put this inside f. So the x has to be able to go into the g, evaluate that, run that through, and then whatever result you get there has to be able to be run through the f function. Think about those boxes that we saw when we introduced functions, right? The g box, x goes into it and something comes out. Whatever comes out there now has to go into f, into the top of the f box. So that's what this domain is talking about here. The domain of f is all real numbers, right? Here, no restrictions. Sometimes we write all real numbers with this capital R with the double line here. G, the domain is the same. That's just a line. No restrictions there. And so the domain of f composed with g, well, there's no issues with either of these. So it's going to be all real numbers. Notice our output here. There's no restrictions on f, on what x can be. Same thing here, that one. This was a kind of basic example because the domain was all real numbers. Let's take a look at this one. Another example here. If f of x is 1 over x and g of x is 4x minus 2 and h of x is 2 over x plus 3, find f composed with g and its domain. F composed with g. I always kind of have to go to regular function notation for it to make sense to me. That means I'm replacing g of x with 4x minus 2, putting that into f. That is going to be 1 over 4x minus 2. We can see here that we are going to have a problem. The domain of g is all real numbers. In interval notation, you would see that negative infinity to infinity. Okay, no problems there. So let's go back up here to see what this said. The domain of f composed with g is the set of all x such that x is in the domain of g, so the inside function, and g of x is in the domain of f. What that means is if anything had to be excluded from G, we'd have to exclude it in the composition. The domain of F composed with G has an issue where 4x minus 2 equals 0. That means 4x minus 2 can't, 4x minus 2 can't equal 0, so 4x can't equal 2, so x cannot equal 1/2. So our answer here is going to be negative infinity to 1/2 union 1/2 to infinity. And the reason for that is this second bullet point up here, or the second condition, g of x has to be in the domain of f. So here's the problem. If x is equal to 1/2, it's okay in G, right? Because when you do G of 1/2, you get 0. That's okay. That's not a problem to get 0 as the real number. That's a real number. The problem is when we try to plug that 0 into f, right? If I asked you to find f of 0, you would say that does not exist. And that's what's happening in this scenario. So the second condition up there is violated when x equals 1/2, which is why we have to exclude it. Typically what I do is I look at the domain of the inside function, see what that is, and then I look at the domain of the result and see if there are any issues with that and combine those. F composed with G of 2. There are two approaches to this. I'm going to show them both to you. F composed with G of 2 means F of G of 2. First, we could find G of 2. G of 2, if G of x is 4x minus 2, would be 4 times 2 minus 2, or 6. And then this is going to be f of 6, replacing G of 2 with 6. Well, f of 6 would be 1 over 6, because f of x was 1 over x. So 1/6 is our answer there. The other option is to say, okay, in part A, we found f of g of x to be 1 over 4x minus 2. So that means f of g of 2 is going to be 1 over 4 times 2 minus 2. And just thinking of that as its own function, which it is. F composed with g is its own function. We plugged in 2, we had no issues, right? No problems plugging 2 into that composition. And we knew that because it was included in the domain in that interval of the domain. Okay. One thing to note here, in F, x could not be 0, but that did not have to be excluded here, because if x equals 0, remember the first thing we do is plug it into G, and the result there gets plugged into F. So it's not a problem for x to be 0 here. F of G of 0 would be f of negative 2, because G of 0 is negative 2, which is negative 1/2, and that's okay. We don't have to worry about the domain of the outside function, only the inside function and then the actual composition. Here's another one, find h of f of x, just to show you one more example. H of f of x, I think it was. I'm going to write these down. F of x was 1 over x. You should have them right, easy for you to access, but I have to scroll here. 2 over x plus 3 are our two functions. One thing to be careful of here, Now our f is the inside function. The second one is the inside function. That means wherever I see an x, this is h of 1 over x. Wherever I see an x in h, I'm going to put this in place of it. So I get 2 over 1 over x plus 3. Just to simplify this a little bit, I am going to multiply by x over x here. We have to distribute that, of course. Go back to our color we were working with. That gives us 2x over 1 plus 3x. Okay, well, let's think about for the domain of this. The domain requires us to look at the inside function. That is this. Domain of f is that x can't be 0. No 0 in the denominator. Then we want to look at any values that cause a problem in the composition. That would be anything where 1 plus 3x is equal to 0. Because if this is our final answer, we clearly cannot have x equals what, negative 1/3? Because that will give us 0 in the denominator. And so we can't have this. So that means we need to combine these two in our domain of our composition. Be negative infinity to negative 1/3. Union negative 1/3 to 0. Union 0 to infinity. Anything less than negative 1/3 is okay. Anything between those two values is okay. And anything bigger than 0 is okay. But if x equals 0, you have a problem before the simplification right here, before we did any simplifying. You have to be able to plug it into that original function, the inside function. And if x equals negative 1/3, let's think about if you plugged negative 1/3 into f of x, you'd get negative 3. Plugging that negative 3 into this function gives you 0 in the denominator, and that's not okay. That's why we have to exclude those two. Last question here about domain and range before we get to an application is, about composition before we get to an application is kind of looking at it the other way. So here is a function where you are given the composition. I want you to think of this as an inside function and an outside function. And you're asked to determine what the inside function is and what the outside function is. This is actually a critical concept for calculus. Those of you going on to calculus, we will use this idea a lot when you get there. So that's why I like to ask this question, thinking about it the other way. The g of x is inside the f of x. Here, if we say g of x equals x squared minus 3x, that's sort of inside what? Inside a square root, right? And that's just going to be the square root of x. Sometimes this is a little weird for students, but if we think about the concept that we are studying here is taking this and replacing the x with that, you do indeed get this guy. So this would be our answer here. G of x is that x squared minus 3x. F of x is just the square root of x, such that when I replace that x in f with x squared minus 3x, I get that composition. It's the idea of the inside function being that x squared minus 3x, the outside function being the square root. Okay, let's take a look. I think this application is the last one here in this section, this little area. Let's take a look at it. I'll wrap this video up. Your screen's, or your computer's screensaver is an expanding circle. The circle starts as a dot in the middle of the screen and expands outward, changing colors as it grows. With a 21-inch screen, you have a viewing area with a 10-inch radius measured from the center diagonally down to a corner. The circle reaches the corners in 4 seconds. Express the area of the circle as a function of time. All right, just counting the area cut off by the edges of the viewing area. Okay. We want to know area, but we want it as a function of time. So we need to think here about the relationship. I think first we want a relationship between radius and time. And then because we know a relationship between area as a function of r, the radius for a circle is pi r squared, right? So if we can find r as a function of time, we could put that in place of the r here, and then we would just have area as a function of just time, meaning our only variable would be time, right? All right, we have a viewing area with a 10-inch radius. The circle reaches the corners in 4 seconds. Relationship between radius and time. Well, clearly we're going to have to look at the radius, the viewing area, radius, and the time that it takes to do that, right? So it takes we get 10 inches in 4 seconds, right? So the rate would be 10 inches for every 4 seconds, or 2.5 inches per second. Okay, and so that means the radius of the circle, if the circle grows at 2.5 inches per second, then the radius of the circle is going to be 2.5 t. Or if we wrote r of t, it's 2.5 t. Here's the idea. Let's suppose we are at 1 second, t is 1 second, then if you get 2.5 inches per second, your result after 1 second, r of 1, needs to be 2.5, right? R of 2 needs to be 5 if you get 2.5 inches per second. R of 3 needs to be 7.5. And so that's what we're multiplying the number of seconds by that rate to tell us how many inches the radius is at any particular time. If I want A of t, I need to do, instead of A of r, I need to do A of r of t. So that's this composition idea. In place of r, I'm going to put this 2.5 t inches, that's the radius. We need to square it. 2.5 times 2.5 is 6.25 t squared. Cleaning that up a little bit, we would most commonly see that as 6.25 pi t squared. So there we have area of the circle as a function of time. Meaning, if I wanted to know what is the area after 2 seconds, what's the area of the circle after 2 seconds, I could say A of 2. 6.25 pi times 2 squared, which is 4, that'd be 25 pi. Okay, 25 pi square inches, right? We're talking about area in inches, square inches. Cool, I like that example. I think it's a pretty cool way to show how composition of functions allows you to convert between one function that we know, say for example, area as a function of radius, area of a circle as a function of radius, to area as a function of a different variable if you know a relationship between that different variable and the one that you originally had. So pretty cool composition application, I think.